Hi, everybody. My name is Bill Troutman, and this is the week 6 live chat. Right now, I just had I was going to cover section 5.1. If I have time, maybe I'll do 5.2 also. Um, but all I really had planned for today was 5.1. Before I begin, Colin, did you have any particular questions about anything? Okay, so I'm going to just cover 5.1 then. Let's take a look. And this is the beginning. It says that the title of this is Basic Set Concepts. So if we take a look at this, um, let's take a look at the two ways of writing sets. They say using the roster method or using set builder method. So uh, the roster method is a list. I'm just going to write down the list. So it says B is a set of all bordering states. So if I use the roster method, I'm going to have the set brackets in here. And I'm going to put all the bordering states of Texas. To tell you the truth, I don't know all the bordering states of Texas. I know Louisiana is a bordering state. Oklahoma borders Texas. When you leave Texas after El Paso, is that New Mexico? I think that's New Mexico. And so on and so on. So this is the roster method where you just list the items. Set builder method is different. Set builder method, you have the set brackets, then you have X with a line through it, and then you say X is a border state. So you don't list them border. If I could, X is a border state. So I mean, you would list. This is called set builder, where you would list what X is. X is a border state. The roster method, you actually list each item. So that's the difference between the roster and the set builder. Set builder, you can write out your answer, but you don't have to list the items. The roster method, you list each individual items. And I'll show you another example of that here. R is a set of integers between -2 and 4 inclusively. So inclusively means -2 and 4 is part of it. The roster method, we're going to list all the integers between -2 and 4 inclusively. Inclusively means -2 is part of that answer. And then the rest of the integers between -2 and 4, you have -1, you have 0, you have 1, you have 2, you have 3, and 4, because they said inclusively. -2 and 4 are part of the answers. The way to write this in set builder, you would write X with a line bar, and then X is between -2 and 4. This is how you would write it, between -2 and 4. Inclusively means -2 and 4 are part of the answers. So this is how you would write it in set builder form. So those two answers, this is the roster method where you list each item in that set. This is a set builder where you list the equation or how you're getting to that answer. All right, so next it says determine which collections are not sets. A collection of former mayors, I guess you can write that as a set if you list them all. Um, these are kind of weird. I'm going to skip these because I don't think these are on the homework, which are not sets. I think they might ask which are not. I think the homework lists them differently. Which, God, I wish I would have opened up the homework now. I don't think they list them like that. Anyway, that's a pretty easy part on the homework when they explain it to you. God, how did they list that? I'm just gonna go to that really quick and see how they list that. Because I know that they use a different word. Well, not for the empty set. No, there's a different word they use for these type of problems. I'm getting there. I'm opening it up right now. Oh, that was that was the homework. So chapter 5.1 is opening. They ask, let's see what it says here. No, they didn't ask that. Determine if it's well defined. They ask if the set is well defined. So I mean, in 3B, is this collection well defined? The 5 best restaurants in San Antonio. No, it's not well defined unless you list them. Um, I'm going to skip those parts, these questions, because these are not on. I'm not quite sure what they're asking for on there, and they're not part of the homework. Let me go to the next page of this, where we're a little bit more, where we have some more questions. So on here, let's take a look at this section now. It's kind of important to know the different symbols we're using. This symbol right here means element. Element. So when we say 3 and this symbol, is 3 an element of this set? In other words, is 3 in that set? Is it part of that set? And the answer is yes, so this is true. Is 5 in this set? This set is 1, 3, 7, and 11. Is 5 a member? Is it an element of this set? And no, that's false. 5 is not an element of that set. This problem is 1, 3, 5. It looks like it's doing all odd numbers: 7, 9, 11, 13, 15, 17. 15 is not an element. So if that's an element, if you have a line through it, that means is not an element. So this statement says 15 is not an element, but it is. It's an odd number within those numbers. So this is a false statement because 15 is an element of that set. 37 is not an element of this set. That's true because the numbers stop at 35. They're all odd, but they stop at 35. So 37 is not in that set. It's not an element of that set. So that's not too bad. Which of the following is the empty set? So there's a couple of ways of writing the empty set. One is like this, with a set with nothing in it. So that's the empty set, a little set with nothing in it. This is not the empty set. This is a set with 0 in it. So that is definitely not a way of writing the empty set. This is a way of writing the empty. Which of the following is the empty set? This is a set. And that symbol means the empty set. So this is the empty set. This is a one way of writing the empty set also. This is just 0, so that's definitely not, it's not even a set. I'm not sure about these. X is a flying pig. If I had to write down, see, this is the set builder. If I had to write down where X is a flying pig, I need to list all the flying pigs. I don't think there's any. So I would say this is an empty set. And, you see things advertised that pigs fly. But I would say there's no flying pig, so that's an empty set. Now, be careful about this next one. I'm going to try to raise it up. Let me try to raise this next one up. This next one here, it says x is, let me write it out. X is greater than 8. So let me list x is greater than 8. Let me list numbers greater than 8. 9, 10, 11, 12, 13, and so on. And x is less than 2. Well, numbers less than 2 are less than or equal to 2, or 2, 1, 0, and so on. And you can put decimal points in there, -1, -2, and so on. And means intersection. So is there an intersection between this group and this group? And there isn't. There's no number that's in common with greater than 8 and less than or equal to 2. So this is the empty set also. So there is nothing in this set because there's nothing that intersects those two. And this is just another way of writing the empty set also. All righty, I'm going to move on. Unless there's a question. And once again, this is section 5.1. Write each of the following sets in roster notation. Once again, roster notation is just listing out the events. The set A is the set of all U.S. states. So if I'm going to list it in roster notation, I'm going to put Alabama, Texas, list all 50 states, Idaho, blah, blah, blah. So I don't know what all 50 states are, but that's the roster method, listing all 50 states. Set B is a set of all natural numbers greater than 7. So a way for me to list all natural numbers greater than 7, natural numbers are whole numbers. The first number greater than 7 is 8, then 9, then 10, then 11. And then you can just put 3 dots after it, and it tells you keep on going. Roster method. X is a natural number. X is an element of a natural number, and X is odd. So a roster method of listing all natural numbers that are odd. Natural numbers are counting numbers starting with 1, 3, 5, 7. Once again, 0 is not natural. Negative numbers are not natural. And then once you show a pattern of all odd numbers like this, you can put 3 dots and they'll know that pattern continues. So that's the roster method, just listing each item in a set. Cardinal number is the number, so we need to write this down, the number of distinct items in a set. So you have the cardinal number, the number of distinct items in a set. So you have to count the number of items in a set, and you cannot repeat. Like, do you see we have 1 twice, but you can only count it once. So if a number repeats, or if an item in a set repeats, you only count it once. So we have 1 item, 2, 3, 4, 5. 5 distinct items. Even though there are 6 numbers in there, we wrote 1 twice. The cardinal number of this set, the cardinal number, and this is how you write cardinal number of this set, is 5. There's 5 distinct items. The cardinal number of an empty set is 0. There are no items in an empty set. The cardinal number, where x is a natural number and x is less than 7. Well, all natural numbers less than 7, 6, 5, 4, 3, 2, 1. 0 is not natural. If you look at the definition of a natural number, whole numbers 1 and greater. So these are the natural numbers less than 7, and there are 6 of them. So the cardinal number of this set is 6. There are 1, 2, 3, 4, 5, 6 of them. And I'm going to move on. Determine if the set is finite or infinite. X is a U.S. state. Well, there's 50 U.S. states, so that's finite. It doesn't go on forever. Infinite means it goes on forever, right? So it is finite. Let's take a look at this next one. Z is greater than 9. Let's start listing numbers greater than 9, 10, 11, 12. And Z is less than 1. 1 less than or equal to 1. So they use the symbol and. This is instead of writing and, they use the symbol and I'm assuming that this and this and does not mean the same thing. I don't think on the homework we would ever do that. This and has no meaning. So pretty much any Z is greater than 9 is an infinite number of numbers, because 9, 10, 11, 12, a million and 3, a million and 5 million, 10 million. You keep on going. So this is an infinite set. It's an infinite set. It has a lot of numbers in it. If X is a natural number greater than 7, once again, natural numbers greater than 7, 8, 9, 10, 11, it goes on forever. That's also infinite. Oh, wait. Yeah. Because they're natural numbers and greater than 7. Numbers greater than 7. These are all natural numbers, and they're greater than 7. So there's an infinite number of. I think they meant something else with this and, so I'm going to leave that alone. I would actually cross that out because I don't like that symbol. It would have been something different if there's an and. And actually, let me clear it off and do it. So let me clear this out for a second. I want to do this if the word and was there, because and means intersection. So X is greater than 9. Greater than 9, these are numbers greater than 9. And Z is less than 1. By the way, Z, it can be any real number. It doesn't tell us in reality. Less than 1 and 1, less than or equal to 1, 0, negative 1. So if you look at this, and the word and means intersection, there's no numbers that intersect. There are no numbers that intersect. So how many answers are there? There are no answers. So this is a finite answer. It doesn't go to infinity. So it is finite if you use the word and in there. So that's a little, I'm not sure why they used the symbol that time. But if the word and was in there, that would be a finite, because the numbers don't go on forever. Equivalent sets and equal sets. We definitely need to write down those definitions or what they are. Oh, but I think I have some more up here. Let me bring this down. Yeah, I do. Let's take a look at these up here. Determine the following sets are equivalent. Okay, so we do need to know the difference between an equivalent set and an equal set. An equivalent set, have the same number of items in a set. That's all they are. They don't have to be the same. They just have to be the same number of items in a set. And equal, somewhere down here we have equal. There we go. Equal sets have the same um, items. Equivalent set have the same number of items. Equal sets have the same items. So that's the difference. So are these equivalent? W is X is a day of the week. The days of the week are Monday, Tuesday, Wednesday. There are 7 days of the week. So there are 7 items in this set. X is the number, X is a month with exactly 31 days. X is a month with exactly 31 days. How many months have 31 days? I don't know. Do you know how many months have 31 days in them? Let's count them. I have a calendar here. I have no idea. I should have a calendar with everything. Let's see. February has 28. The 31 is March 1. April has no. May has 31. 2. January has 31. 3. October has 31. 4. November, no. December, 5. So I think there are 5 months with 31 days, Boy, that's a hard one. And do you see how this has 5 things in the set? This has 7. So they're not equivalent. Not equivalent. They have to have the same number of items. X is a planet in our solar system. X is a current U.S. coin and has a value of less than $1. X is a planet. How many planets are in our solar system? I don't know. Aren't there 7 or 13? Colin, you know how many planets there are? 9 planets, maybe. I don't know. X is a U.S. coin that has a value less than $1. We have a 50-cent piece. We have a 25-cent piece. We have 10 cent. We have a nickel. We have a penny. That's 5. I don't think we have any other values less than $1. So there's 5 there. There's 9 planets. So they're not equivalent. They're not equivalent. Equivalent sets have the same number of items. So that's an equivalent set. Not only do they have the same number of items, I think you can't count an item twice. Yeah, same as a cardinal number. You can't repeat the item twice, or you can repeat the item twice and it only counts once. So if we look at these 2 sets, you can look at I guess you can say equivalent have the same cardinal number. That might even be better. Equivalent have the same cardinal number. Remember, cardinal numbers, if you have 4 4s, you only count it once. 2 3s, you only count it once. Here's a 2 that counts once. Here's a 1 that counts once, and here's a 0 that counts once. So the cardinal number for this is 1, 2, 3, 4, 5. There's 5 elements in there. If you look at the bottom, there are 5 elements. So these 2 sets are equivalent because they have the same number, the same cardinal number. Now, they're also equal because they have the same items, the same actual elements, 4, 3, 2, 1, and 0. Here we have 4, 3, 2, 1, and 0. So that set is equivalent and equal. Now, if we look at this set here, x is greater than 7 but less than 10. If you write this out, 7 is inclusive. It has the equal sign. So 7, 8, 9, but not 10 because 10 doesn't have an equal sign. Set D says 7, but there's no equal sign, so it starts at 8, 9, and 10. So these two sets are not equal. These two sets are not, if I could write it equal, these two sets are not equal because they have different numbers in them. That has 7, 8, 9. This has 8, 9, 10. However, they are equivalent because they have the same cardinal number. There are 3 numbers in this set. The cardinal number of this is 3, and the cardinal number of this set is 3. So they are equivalent, yes, but they're not equal. Equal means they have the same items in there. This has a 10. This one does not have a 10. So equivalent have the same cardinal number. Equal have the same items in the set. This first section is hard to get through. It is just, that's it. That's section 5.1. Let me hit stop for a second.